Okay, in this example of paired data, we have a shoe manufacturer who claims that athletes can increase their vertical jump heights using the manufacturer's training shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the training shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown in the table. Assuming the vertical jump heights are normally distributed, is there enough evidence to support the manufacturer's claim at 10% alpha? So this is the first time we've had a 10% alpha. Okay, so our information in my math lab, you would get something very similar to this, but you probably wouldn't have this row for differences. Our original jump height, the manufacturer is assuming the original jump height will be less than the new jumping height. So I want us to be aware of that when we set up and put information into StatCrunch. The other thing that we need to be aware of is how do we state our HO and our HA. Our null hypothesis is that the average difference is going to be equal to 0. If these shoes made no impact at all, one might be up, the other one might be down, and that would all average out to be 0. But the manufacturer is claiming that the average difference in jumping height will be greater than 0. So that's his claim. Okay. Our confidence level is 90%. Alpha is at 10, and we've got that from here. This is a right tail test from this sign right here. Our sample size is 8, our degrees of freedom is 7, and our critical value is 1.415, and I got that from looking at the t-table. We had a degrees of freedom of 7, being we had a sample size of 8, and this is a one-tailed probability at 10% alpha, so that would come down to, that intersects here, 1.415. Okay, so I pointed out that we're assuming the manufacturer is thinking the outcome is going to be greater than 0. That would be implying that I'm taking 26 minus 24. So I would probably switch the signs on each of these differences and identify that my sample 1 is going to be 26, or is going to be the new jumping height, and my sample 2 is going to be the 24 in this case, or the original jumping height. Just because I want my differences to be positive, that makes a little more sense in our claim. I'm going to go to StatCrunch and do this in StatCrunch. Okay, so I put the information in the way it would spill in, the way my math lab would spill it into StatCrunch. I'm going to hit Stats, go down to T-Stats, down to Paired. Now again, I'm going to put sample 1 as my variable 2. Sample 2 is going to be my variable 1. My original jumping height is in sample 2. My outcome jumping height is in sample 1. I don't care where they go, so I'm just going to leave that optional. I want to save the differences because I'm going to come back and look at that. I'm assuming that the outcome is going to be greater when I look at these differences. So I can come down here and hit Compute. It does give us the mean of 1.75, and that's not a bad increase in jumping height over an 8-month period. Our t-stat is 2.3 with a p-value of 0.0262. So that t-stat is much higher than the 1.4, which tells us it's probably outside of the range and it's going to be in the rejection zone. The p-value is low. Again, the null must go. So both of those are going to support that we would not support the null hypothesis. Being I'm in here, I'm going to go ahead and show you options. I'm going to go ahead and do the confidence interval. So I come down here and do the confidence interval. And if you remember, this was a one-tail test. We had alpha 10. All 10% of that alpha was in that right tail. The confidence interval is a two-tailed event, and the confidence interval that would have 10 alpha in each tail would be a confidence interval of 0.8. So I need to clarify that here. So I go and click Compute, and I come up with a lower limit of 0.688 inches to an upper limit of 2.81 inches. So we feel like we are 90% confident, or 80, should say 80% confident, that our average jumping increase in jumping height is going to fall in that interval. 0 is not in that interval, so it must be that this does increase jumping heights. I have no idea, but I think that your my math lab might ask for the standard deviation of the differences, and to get that you're going to have to do the summary stats here for the difference column. And I have no idea why that's popping up twice, but I go ahead and I click on that compute to get the standard deviation there of 2.1213. You would also need that if you were doing this by hand. So I'm going to go back to our problem and we'll finish it out by hand. Again, our average difference was 1.75. We're assuming, or we're testing the difference, an average difference of 0, so I'm plugging in 0 there. The average of the standard deviation, or the standard deviation of the difference was 2.123. Square root of 8 is the other part of that. Adjusted standard deviation, we come up with 2.33, just like we did before. This is on row 7 of the table. This value is between the 0.05 and 0.025. So if you don't have StatCrunch, you would go back to the table and look at where would 2.33 fall on that table. So when I'm looking at this row, for 10%, 2.33 is going to end up, well, over here, right here, between 0.025 and 0.05 for one probability, right in here. Okay, so back to our chart here. When we draw our critical value, we can visually see that the test statistic falls out in that rejection zone, far to the right of the critical value. Our p-value, again, we got from StatCrunch. P-value is low, so the null must go. When we do the confidence interval, when we're plugging in our average difference plus or minus our critical value times our standard deviation divided by the square root of our sample size, we came up with a lower limit of 0.689 inches, an upper limit of 2.811 inches. So all three of those methods support that we are going to reject the null hypothesis. There is sufficient evidence to support the shoe manufacturer's claim that his shoes are effective in increasing and improving the jumping height of athletes.